Now I want to go back to the potential energy and get little more feel for it. Although I am going to restrict myself in one dimension, it teaches me a lot. Suppose there is a potential energy curve like this. So this is u x versus x. I can simulate this by taking a wire in this shape and let a bead move over it, because the height would be proportional to the potential energy because of the gravitational force. There are different points I want to identify in this. This is the maximum of potential energy, where I have du dx is equal to 0 and d2u over dx square less than 0. There is this point where I have du dx is equal to 0, and this is a minimum, and therefore d2u dx square is greater than 0. At this place du dx is less than 0, on this place du dx is greater than 0. So let us look at these 4 points and see what I can say about them. Let us start with the maximum of the potential energy, where I had du dx equals 0 and d2u over dx square is less than 0. So you notice, since it is 0 here, du dx on this side, d2 du dx is 0, and as x goes up, since d2u dx square is less than 0, du dx on this side must be greater than 0, as is also evident from the graph. Similarly, on this side du dx is less than 0. So if I were to look at the force F x, which is equal to minus du dx, you can see that on both the sides the force will be pointing away from the maximum. So looking at the maximum, I see that the force points away from the maximum of potential energy. So any particle at the maximum of the potential energy is going to be running away from it. Let us look at the minimum, or a minimum. At a minimum, du dx is again 0 and d2u dx square is greater than 0, and therefore from as you go towards the positive x side, slope is positive, on this side slope is negative, and therefore Fx, which is minus du dx, is going to give you a force on this side, which is going to be towards this, is going to be less than 0 for x greater than x min, and is going to be greater than 0 for x less than x min. So you see the force points in the positive direction if you go to the left of minimum, and in negative direction if you go to the right of the minimum. Therefore the force always points towards a minimum. So let us write the force points towards the minimum of the potential energy. So any particle at the minimum would tend to move towards the minimum if displaced from there. So let us see now, if I had a curve like I plotted earlier, what would happen? If I had a particle here, it will just come down this way or this way. If I had a particle here, if I displace, it will come down back to the minimum. At these points, the force is in this direction. At this point, the force is in this direction. At this point, the force is in this direction. This is F, F, F. F is always opposite to the slope. One interesting thing that comes about then is if you are at a minimum and particle is displaced from it, it tends to come back. In fact, if the displacement is very small, you will see that it will start performing simple harmonic motion. Let me explain that. So, near a minimum, and let us call that minimum x equals x0, let us take this one. I have u x slightly away from the minimum as by Taylor series expansion u x 0 plus du dx at x 0 x minus x 0 plus 1/2 d2u dx square at x 0 x minus x 0 square. Since this is a minimum, du dx at this point vanishes, and therefore I have u x as equal to u x 0 plus 1/2 d2u dx square at x 0 x minus x 0 square, and therefore the difference in the potential energy u x minus u x 0 is equal to 1/2. This being a minimum is a positive quantity, so let me write this as k x minus x 0 square for small displacements. If I call this u y by taking u at x 0 to be 0, because as I said earlier, you always define potential energy with respect to a particular point, is equal to 1/2 k y square, where y I take to be x minus x 0 or the displacement from the minimum. You can see that the potential energy changes like a spring, and therefore any particle displaced from here would execute simple harmonic motion with the characteristic frequency of k over m, where k is given by d2u dx or the second derivative of the potential energy, and this is going to be square root of 1 over m d2u dx square at x 0. So, what we have done in this lecture is try to eliminate the time from the equation of motion, and consequently we found that we can relate certain quantities which depend on the position. These quantities are energy, kinetic energy or the potential energy, to evaluate the velocities at different positions. We also discussed in short, very briefly, what the conservative and non-conservative forces are. We have restricted ourselves to one-dimensional motion in this case, and the next lecture I am going to generalize to three-dimensional motion and see how really we can answer the question whether a force field is going to be conservative or non-conservative.